When I first started working with LLMs, I thought the hard part was choosing the right model. That should I choose ChatGPT, Claude, or Gemini for what task, what to do, what requirements to meet. Then I get to know that fine tuning, prompt engineering, temperature settings may help it perform better. But nobody told me that one of the most important things is that the model doesn't have access to the right information at the first place. And that context matters the most. The most AI tutorials skip this major problem, and this one won't. This video is part of my ongoing Decoding AI series. In its last video, we have just covered the difference between prompt engineering, context engineering, and even harness engineering. Video link to the I button. You can check it out. And most important, if you are new here, welcome. I am Harshita Kathuria, Associate Software Engineer at ServiceNow. And on this channel, we go beyond the hype and into the actual engineering behind AI and scalable systems, the real problems, the real failures, and today we are talking about one of the most important concepts in the modern AI engineering, that's RAG architecture. So let's get into it. Before understanding what is RAG, why it's an important concept, and why we are learning RAG architecture right here, let's first understand why LLMs fail in enterprise. Every LLM you have ever used, like ChatGPT, Claude, Gemini, was frozen in a moment the training ended. It knows nothing about your company's data, nothing about what happened last week, our private conversations, or our internal policies, or your customers' new requirements, or your new system setting up in your company, new environments. So basically, it is not updated with the newer information, newer facts we might need in our inclusion of the tasks. So this isn't a small problem. And even Stanford research found that LLMs hallucinate between 15 to 20% of the time on the factual queries when they have no external grounding. And you can say one in out of five answers are there wrong, and they answer it very confidently. IBM found that 72% of the AI failures in enterprise settings come down to inadequate context, not model capability. The model isn't the problem, the missing information is. No matter how powerful these models become, they all share these three fundamental limitations. The one is the knowledge cutoff. They have knowledge cutoff. So, obtain specific amount of information already in their memory, which we call as pre-trained information or pre-trained data. Second, they can hallucinate. They won't let you know that they do not know about specific answer. They'll just give you some random information they thought of, and they don't know anything about your private company data or what we have discussed, the newer data. So when someone asks inside your company what's a queue for revenue, even the smartest model in the world draws a blank because the information was never a part of the training data. That's not a bug you can patch, that's the ceiling of what base language model can do on its own. And that's exactly where retrieval augmented generation RAG was invented. We get to know model isn't broken, the context is missing. So we shifted to a RAG architecture. Now the question arises where RAG came from. RAG wasn't invented by a startup trying to sell you a product. It was introduced in 2020 research paper by Patrick and his team at Meta AI and formally titled Retrieval Augmented Generation for Knowledge Intensive NLP Tasks. The paper showed that models using RAG achieved state of art results on knowledge intensive tasks, outperforming models that relied purely on what they memorized during the training. That one paper completely changed how enterprise AI get built. Today, we are going to break down how RAG works, why it became the foundation of the AI coming up, enterprise AI, and every developer preparing for AI engineer role, LLM engineer role, or applied AI roles should know about it. It is getting highly adopted in an enterprise AI. Let's understand RAG within a simple analogy. Think of a base language model as a brilliant student who has studied millions of books, documents, websites, articles. They understand language, reasonings, and patterns incredibly well. But during the exam, they are not allowed to touch even a book, new or document, that's it. So the question is that about something they have, if they have asked something about they have learned or they have known before, they have addressed that problem before, they'll probably answer well. But if the question is somewhat twisted, new, or something private or highly specialized, they can only guess. And that's where hallucination comes in. Now imagine giving the same students access to textbooks, even a whole library, company manuals, newer research papers, databases during the exam. Suddenly it becomes an open book exam. The student doesn't need to guess anymore. They can look up the answer before responding. That's essentially what RAG does. Instead of forcing an LLM to rely solely on its training data, RAG allows it to retrieve the external information or the relevant information from the external knowledge base provided by your company or you specifically working for a project you provide in your local base. So that RAG can basically that LLM can use that information or that knowledge base via RAG before generating a particular answer. Let's get deeper into the high-level architecture of a RAG. A production RAG pipeline typically looks something like this. And what do we do? In this pipeline, documents comes in, which could be in a form of anything like PDF, Confluence, Notion, or Wikipedia's. That documents gets broken into pieces, means they get chunked. And those embeddings and those chunks are further converted into our embeddings. So we do say embeddings are created. And then those embeddings go into our vector database. So now we have our documents. We have the relevant information from all of the documents chunked, then created into the embeddings and stored into our vector bases in the form of embeddings. Right? So, what will happen in the flow when a query arrives, when a user sends a query, right? The retrieval happens. We'll do the embedding of the query also. Embedding is nothing but a mathematical representation of text. We'll create a embedding of a user query, and that query embedding will be sent to our retrieval system for the retrieval process. And the results, whatever the results we get, those gets re-ranked from our database. Whatever is retrieved will be re-ranked, that which is the most relevant one. That re-ranked information is further sent with prompt augmentation, means it will be attached to our prompt as an context and further sent to our LLM to generate the answer. Let's start with the step 1, document ingestion and chunking. Now we have understood that data is the key, An organization might have their private data, their own PDF, their own research paper, their internal stack information, their support tickets, their own knowledge bases. The first instinct is usually why not just store the entire documents, because retrieval systems work much better on smaller pieces of information. 100 pages PDF might become 500 individual chunks. This process is called chunking. And surprisingly, chunking is one of the most important decisions in our RAG systems. Experienced AI engineers are often spend time optimizing chunking strategies. The simplest approach is fixed chunking. You split the text every few hundred tokens. It's easy, it's fast, but it often breaks the context. Imagine cutting a sentence in half simply because you reached the token limit. There's where we face the context loss. The smarter approach is the semantic chunking. Instead of splitting based on a size, the system split when the topic changes. This preserves the meaning and usually improves the retrieval quality. And there is a hierarchical chunking, one of the most common production approaches. One version is broken in small, precise sections for search, and the other keeps the largest sections for reading and understanding. The system searches using the small chunks but returns the large context to the language model. That gives you both retrieval precision and contextual understanding. That's the reason why our senior engineers are obsessed over chunking. After understanding chunking, now we need a way for machine to understand its meaning. This is where embeddings come in. An embedding is simply a numerical representation of a text, but instead of thinking about thousands of dimensions, here's a more intuitive way to think about it. Imagine GPS coordinates for meaning. Text discussing similar ideas in the nearby neighborhood. Text discussing completely different topics ends up apart, like this: football and quantum physics are way apart. For example, what causes inflation and why prices are increasing? Use completely different words, but their meanings are extremely similar. So their embeddings end up close together. This allows systems to search by meaning rather than exact wording. That's the significant advancement. Once the embeddings are created, now there should be a way of storing that embeddings or that meanings, contextual, semantic meanings somewhere. That's where our vector databases come in. We do have some famous examples like Pinecone, Viviate, Quadrant, Melvus, Chroma as the popular vector databases used in our enterprise AI. And vector databases basically perform similarity search, whereas our traditional databases just do keyword matchings. So instead of asking, do these words match, they ask which documents are closest in meaning. That's the fundamentally different way of searching information, which helps us segregate the information based on the meaning, or that can make our information more relevant in terms of our use case, retrieval. So, if I want to understand retrieval, let's take an example. For example, you are walking into a library, we are having a 10 million books in a library, and you don't want to read every book. You want an export librarian to come and help you find out the first 5 most relevant books and place them on the desk. This is what retrieval does. The retrieval system acts as a librarian, and its job is to find the most relevant information as quickly as possible. Once that job is done, you have the relevant information in your hand. And that relevant information, relevant chunks, are then added to your prompt as in a context. And further, that context is provided to the model, which is called augmented prompt. And this stage is called augmentation stage. And this now the model is no longer relying solely on its memory. Now it has evidence. We can say that it now our model knows the context, the retrieved documents, question, the user's query, and the instructions already passed to the system, which creates a response. And finally, the language model generates a response when we get a response. This is the part which the most people think that it's an interesting part, but it's the least interesting parts because nothing is that important here because all the job is done before. The retrieval, we can say that researcher's job, the journalist's job, the investigators, and the fact checkers working behind the scenes. That's our RAG system. Retrieval is our research team, and LLM is our news anchor. If the retrieval fails, even the smartest model do not have the context of the relevant information you are asking about. So that can't even give a good answer if it's not trained on it and do not have the context. So this is how our whole RAG works. Common argument today is models can perform millions of tokens now. Doesn't that make RAG obsolete? Not really. Three reasons. First is cost. Sending huge amount of context like the complete knowledge base of company, then every query includes entire information and cost becomes unsustainable very quickly. Second one, latency. Larger prompts requires more processing. Users expects responses in seconds, not minutes. Third, this leads us to one of the most famous AI concepts in modern AI, the needle in haystack problem. Imagine hiding a single sentence inside two entire novels. Now ask someone to find that sentence instantly. Even human would struggle. LLMs face the exact problem. As context grows, loading the specific pieces of information becomes harder. The RAG solves this by finding the needle first and then showing it to model. Instead of giving the model the entire haystack, and it only receives the information that matters. Building a RAG demo is easy, building a production RAG system is not. This is where most engineer effort actually goes. Hybrid search. Semantic search is powerful, but sometimes exact keywords matters. Suppose you are searching for product IDs, invoice numbers, error codes, serial numbers. Semantic similarity alone may not be enough. Production systems often combine semantic search with keyword search. This is called hybrid search and it's used extensively in enterprise environments. Reranking. Retrieval isn't perfect. The top retrieved chunks aren't always the best ones. That's why many systems use re-rankers. The retriever might find 20 candidate documents. A re-ranker reorders them based on the relevance before sending them to the LLM. This often improves the answer quality of the LLM very significantly. HyDE, hypothetical document embedding. This one is particularly clever. Normally, we embed the user's question. HyDE takes a different approach. It first asks model to generate a hypothetical answer. Hypothetical answer is then embedded and used for retrieval. Why? Because answers often resemble the structure of the document more closely than the questions do. As a result, retrieval quality can improve substantially. Query decomposition. What happens when a user asks compare gold prices, silver prices, platinum prices throughout the 2025 and explain the reasons behind each trend? That's exactly multiple questions. Modern system often breaks on large questions into smaller queries. Each sub-question performs its own retrieval. The results are then combined into the final answer. This dramatically improves the retrieval quality for the complex queries. Most production teams spend enormous effort on evaluation. You will just say why? Because how do we actually get to know that our RAG system is working or not? And that can be only done by evaluating some of the metrics or making a criteria against the system, right? So if we get into the criteria, it's we'll check for precision, recall, groundedness of the system, relevance, and even the hallucination rate. Many organizations now uses LLM judges to automatically score outputs against predefined criteria. In modern AI engineering, evaluation is often more important than the model selection. Evaluation isn't optional, it's essential. It is the difference between a demo and a production system. And it's very important. Basic RAG is only the beginning. Our modern enterprise systems have evolved considerably well. You can see the graph RAG, which is bringing up the relationships between people, organization, products, documents, events. This even enables the reasoning across connected information rather than the individual passengers. And you know that our company's enterprise data contains charts, tables, images, diagrams. So our RAG also should be able to retrieve all that kind of data, not just plain text. It brings up our multimodal RAG. And when the RAG system introduces an evaluation step, right? It evaluates. So we might want it to self-check its performance, right? And just retrieve documents are actually relevant or not before generating the answer. It shows up our corrective RAG. If the confidence is low, basically it retrieves again. And the last, self-RAG. It's even more intuitive and more efficient. The model evaluates its own reasoning during the generation. It can identify missing evidence, request additional retrieval, and refine its answer before responding. This creates more grounded and more reliable outputs. And this is the best out of what we can do of existing RAGs. The next major evolution it is Agentic RAG. The traditional RAG follows a simple pattern: retrieve, then answer. Agentic systems are much more dynamic. They can plan, they can search repeatedly, use tools, verify information, refine queries, evaluate results, and then answer. Instead of performing a single search, the system actively reasons about what information it needs. It becomes less like a lookup and more like a researcher. And this is the direction most enterprise AI systems are moving today. So that's it for the video. If you stayed till this point, I hope you understand some things better than you did before. And if you genuinely liked the video, hit the like button and make sure you subscribe to follow me along in this series. See you in the next video. Till then, bye bye.